Cambridge IGCSE 0625/42, October-November 2024, Paper 4, Theory, Extended. A rocket has an initial mass of 7.4 times 10 to the power 6 kilograms. Calculate the initial weight of the rocket. So here we will use W is equal to mg. So we have the mass here, which is 7.4 10 to the power 6 times g, and it's given to us in the instructions as 9.8. 7.3 into 10 to the power 7 newtons. Define in words the term weight. Weight is the gravitational force acting on a mass. Figure 1.1 shows a part of a speed-time graph for the rocket as it leaves the ground and travels into space. A speed-time graph is given, and we are asked to describe the motion of the rocket. So from O to A. O to A, as you can see, the gradient is increasing. So if we draw a tangent here and we compare it to a tangent we draw here, you can see the second tangent is more steeper than the first one. So we can see that the gradient is increasing. Therefore, the acceleration is increasing because the gradient of a speed-time graph is acceleration. From A to B, you can see the acceleration is uniform. You can see the gradient is uniform. Therefore, the acceleration is uniform. So that's it for this part of the question. Draw a tangent to the graph at time equal to 400 seconds and use this to calculate the acceleration of the rocket at this time. Show your working. Okay, so when it's 400 seconds, we have to draw a tangent. Okay. So this is the 400 seconds point, and we are supposed to draw a tangent. And try to make the tangent as big as possible so you can reduce the error. So we have to select 2 points. So these are the 2 points we have here, and now we have to work out the gradient. So it's y2 minus y1 over x2 minus x1. So and the answer is 17.5 meters per second squared. Rockets are used to launch satellites into the space. When satellite is released, the rocket returns to Earth. Explain in terms of forces why the rocket reaches terminal velocity as it travels through the atmosphere back into Earth. As the rocket falls, the air resistance increases as its velocity increases. Eventually, air resistance becomes equal to the gravitational force, so the resultant force becomes zero. Question 2. Figure 2.1 shows a golfer about to hit a golf ball with a golf club. The initial momentum of the golf ball is zero. Define momentum. Momentum is a product of mass and velocity. The golf club is in contact with the ball for 5 into 10 to the power minus 4 seconds. The velocity of the golf ball as it leaves the golf club is 41 meters per second. The golf ball has a mass of 0.046 kilograms. Calculate the impulse of the golf ball. So here, the impulse is equal to the change in momentum. So the initial velocity is 0. As you can see, the initial momentum here is 0, therefore the initial velocity is also 0. So The mass of the golf ball is 0.046 multiplied by the velocity, which is 41, and that would give you the impulse, 1.9 Newton seconds. And calculate the force applied to the ball by the golf club. So here we are supposed to find the force, and there's another equation of impulse where impulse is equal to force into time. And we have calculated the impulse in the previous part, therefore we can calculate the force by dividing the impulse by time. And the time is 5 into 10 to the power minus 4. And that would give us the force. And the force is 3,800 newtons. Question 3. State two energy sources for which radiation from the sun is the main source of energy: fossil fuel and hydroelectric. A wind turbine is used to generate electricity. The useful output from the turbine in 1 second is 6,000 joules. The kinetic energy of the wind hitting the turbine in 1 second is 11,000 joules. The velocity of the wind hitting the turbine is 6.3 meters per second. Show that the mass of air hitting the turbine each second is approximately 550 kilograms. So we asked to find the mass, and in the question there's a clue, and that's kinetic energy. So kinetic energy equation has mass, and they have given all the other necessary data as well. So we can use kinetic energy equation and we can work out the mass. And that would give us 554.295, and that's approximately 550. Calculate the efficiency of the turbines. You may assume all the kinetic energy stored in the wind is transferred to the turbine. Okay, so here we know the output is 6,000 joules and the kinetic energy hitting is 11,000 joules. So we can use useful output, which is 6,000 over the total input times 100. Yeah, they asked in the percentage, so times 100. So it's 6,000 divided by 11,000. That's 54.5, 55%. The units given. Tidal energy and wind energy are both renewable energy resources. Suggest one reason why tidal energy is more useful energy resource than wind energy. Ignore the cost of the construction and maintenance. So tides follow a more predictable and regular pattern. Question 4. Figure 4.1 shows a pressure cooker on an electric heating element. The cooker has a tight fitting lid. The pressure cooker is half full of water. As the water is heated, some water evaporates before boiling. Describe the difference between evaporation and boiling of water in the cooker. Evaporation happens at the surface of the water. Boiling happens at a specific temperature. As the water is heated, the pressure of the gas inside the cooker increases. Explain this increase in terms of particles. As the water is heated, the gas particles gain kinetic energy. This causes them to collide more frequently with the walls of the cooker. Each collision exerts more force on the walls because the particles are moving faster. As a result, the total force of the collisions increases. Since pressure is equal to force divided by area, the pressure inside the cooker increases. And this question, right, the how gas particles exert a pressure on the walls of the container, this is a pretty frequently asked question, so it's important that you know the points and you could adapt to different questions and different scenarios and write the answer. Question 5. On a sunny day, the temperature of the black tarmac road and the air above the road increases. Explain why the surface temperature of the tarmac increases. The tarmac absorbs infrared radiation emitted from the sun. causing its surface temperature to rise. This absorption of energy increases the internal energy of the tarmac, making it hotter. Part B. State the method of thermal energy transfer from the tarmac to the air immediately above the road. Conduction. Part C. State the main method of thermal energy transfer from the air immediately above the road to the rest of the air. Convection. Part D. Explain why the surface temperature of the tarmac is higher than the surrounding air temperature. The surface temperature of the tarmac is higher than the surrounding air because black tarmac is a better absorber of radiation than air. Also, tarmac is a poor emitter of radiation at low temperatures, so it retains more heat. Question 6. Student plays violin near the doorway to a large room. Figure 6.1 shows a young teacher standing where he can hear the student but cannot see. State the wave effect that allows the young teacher to hear the sound from the violin at the position he is standing. So the student is here and the teacher is here and there's a gap. So basically the sound waves diffract and the teacher can hear the student playing the violin. Calculate the frequency of the sound with a wavelength of 0.75 meters. The speed of the wave in air is 340 meters per second. So we are supposed to find the frequency. We can use this equation. The frequency is 450 Hertz. Violin produces sounds in the frequency range of 20 Hz to 3800 Hz. The width of the open doorway is 0.75 meters. Explain why the young teacher hears a frequency calculated in A2 clearly but finds a frequency of 3500 Hz much harder to hear. The teacher hears the frequency calculated in A2 clearly because the wavelength of that frequency is similar to the width of the doorway, causing large diffraction of the waves. However, the frequency of 3500 Hz is much shorter than the wavelength, so there's less diffraction around the doorway, making it harder to hear. When the wavelength and the width of the door is almost the same, the diffraction is maximum. Therefore, the teacher can hear the student playing the violin. Part B. A plane mirror is placed at point X so that the teacher can see the student on figure 6.1. Draw a ray of light from the violin to the point X and from point X to the teacher. Draw and label the mirror. How teacher sees the students. Okay, so here we are supposed to draw a mirror at point X. And we will draw normal here. And from the student. And here the ray goes to the teacher. So here the angle of incidence is equal to the angle of reflection.